Okay. Crowding is the idea of, okay, fitness sharing is the idea that individuals with similar fitness are likely similar, which is entirely not true in general, but it might be a quick and dirty heuristic to give you a sense of what's similar. The reason it's, like if I have two permutations of TSP that are nearly identical, maybe they've got like one or two cities swapped, they're probably going to have similar-ish fitnesses compared to one that's all over the place. But then again, I might have entirely different permutations with very similar fitness values as well. So this isn't a silver bullet trick, but if we go in with that idea, we can kind of use this to our advantage of like somehow maybe using similar fitness values as a proxy for measuring similarity or that diversity level. There's fancy math that goes with it. Crowding, it's similar, but like if we're doing that selection strategy and we want to replace someone, so if this is like a steady state one where we need to both select the parents and then select who we're replacing, maybe we should replace ones that are most similar to it. Because if we end up replacing people that are individuals in that population that are very different, well, suddenly we're making more of the same in the population, which might be good, might be bad. Remember, all of these things are competing. There's like 100 dials on our algorithm that we can tune. And as soon as you change one, it affects another and all over the place. It's typical for steady state. Yeah, that doesn't matter. Automatic speciation. So this is the idea, and we talked about this already, kind of in terms of that ring species idea. Maybe we only allow species within the population to mate with one another, to produce offspring. This would be the idea that, well, if they're similar, maybe we should let them reproduce as opposed to things that are very different. Or maybe that's a terrible idea in your context. These are just ideas that might be great for what you're doing. How? We can use measures in genotype space or phenotype space. Think of that difference between the zeros and ones and the counting up, maximizing the integer based on the binary representation. How similar are they in genotype space? Well, that might be like a Hamming distance. How similar are they in phenotype space? Will actually be the difference. Have a bit flag attached to individuals to represent their species, whatever. Ring species. Island model, I think we talked about this last time. If you have 1, 2, 3, 4, 5, okay. If you have an 8-core processor, great idea is have eight islands, have them run independently, and then periodically allow migrations between the islands. So they get a chance to kind of, they do their thing, but ideally maybe the islands kind of evolve down different pathways, and then if there's migration, suddenly we're adding way more diversity. But then we have way more parameters to tune. How many islands? How often do you allow migrations? How many do you allow to migrate? A lot of questions, but these are all just things that you can play with. Yeah?
I was going to ask, related to the phenotype, you said it is a representation of an answer. Does that mean it could be a fitness or something different?
The phenotype is like what the genotype means. So TSP, genotype is the permutation. It is like 0, 1, 7, 14, 2. Phenotype is like, well, what does that mean? Well, that's a very direct representation of, well, it's easy to go from this permutation to what it means in real life, which is like the order that you visit the cities. It's effectively the same. But there are cases where, like the 0 and 1 representation, where the genotype was a bit string, that's the genotype. Then the phenotype was what it meant in terms of in decimal value. So we use those words to describe like which version we're talking about. Are we talking about the encoding or about what the encoding means? Now the fitness function comes into play on evaluating this in the context of what it would mean in the phenotype space. Yeah?
That last bit, you lost me.
Can you be more specific?
Last sentence or so. Perfect.
Yeah, so the fitness function is, like if we're measuring the bit strings, right? And I want to put it in the context of like, well, what it means. And this isn't even true in general, but if I'm evaluating that, I need to like convert it to the binary one, and then the fitness is just, well, bigger is better. So the fitness function is dependent on the representation because, well, that's like what we are evaluating, but it's separate because in the context of when we're talking about genotype and phenotype. I think you're thinking too hard. Genotype is the encoding, phenotype is what that encoding means for the problem we're solving. Yeah.
So are we effectively then running a bunch of different algorithms in parallel to one another? And if that's the case, could you also split could you parallelize within the CPU and also utilize like the GPU as well? Like maybe like have those running parallel?
I would recommend against that because in a perfect world, yes. But so a lot of people in the context of like, oh, we know we use GPU for machine learning. Well, GPU for machine learning, fantastic. But the reason GPUs work really well in like neural networks is because GPUs are full of a bunch of simplification. A lot of very simple, stupid processors that are just really good at one thing. Floating point number calculations. Because that's what they do for graphics. But that's all like a neural network is. Just crunching some simple numbers, right? It's got a small instruction set compared to like your x86 architecture. So we have all these simple number crunching, so it's great for neural networks because that's all it is. Evolutionary algorithms are different, and how you make use of the GPU would require a lot more wrestling with the GPU. And then on top of it, I wouldn't be surprised, at least in my experience, maybe things are way better now. Doubt it. When you make use of a GPU for evolutionary computation, unless you have like massive population sizes, like hilarious, and just hilariously large runtimes where you don't even like allow migrations or something, all of the communication between the GPU and the CPU is going to be the bottleneck. You're going to get way slowdowns there to the point of it being you're worse off. Because there's also scheduling as well. So you use C#. Anyone else use C#? Once. It's there's probably something similar to it in other languages. It's just I know it in C#. There's a like parallel for each loop. So if you have a population and you want to run the fitness evaluation in like a for loop, well, do individual 0, then 1, then 2. Well, you can say parallel for each loop and it'll automatically go distribute across your processors, not GPU. In this case, you don't need to, depending on how you build this, so now we're talking more about of an engineering design question. Depending on how you do this, so if I have 8 islands, and I want them to run in parallel, some fitness evaluations might be easier to do than others, depending on the evolutionary computation thing we're doing, like especially in genetic programming. So some islands might get way ahead of others in terms of the number of generations they've done. So how you manage the migrations can become challenging. Because if you say like, okay, run for 10,000 generations and then do migrations. Well, maybe one island gets done really quick, or maybe 7 out of your 8 islands get finished real quick and then there's one that's lagging behind. Now you've got a lot of wasted processing time. So what people will do is instead of actually parallelizing it, they will just run 8 GAs at the same time with the island model. And then you're not really wasting any resources. You just say, okay, run, all these single-threaded things, but just 8 of them at the same time. There. It's parallel. Good question, though. And then I think I saw a question over here somewhere. No? Was it you? No? All right. Island model, yeah. How often do we migrate? Too fast, we might converge too quickly. You don't really get the benefit of the islands. Too slow, well, you're wasting time. How many individuals do you migrate? I don't know. If it's too many, maybe it'll have this effect. Too few, it'll have that effect, right? Do we do a full shuffle? Maybe 4 or 5. Full shuffle is the idea of like, well, every 10,000 generations, you just put them all together, shuffle them, and put them back in islands. That's a pretty extreme version of migration, where you might have an alternative like 2 or 5 switching between every so often. All just different ideas. Remember, everything in the context of evolutionary computation, no matter what anyone tells you except me, listen to me, is ideas. Then take your ideas and do it. Nothing you do is wrong in the context of building your GA, barring like bugs and whatnot, of course. But if your ideas are rational, they might not work, but that doesn't mean that you're wrong. Do you know what I mean? Like, do you know what I mean when I say that? I don't care if you're like, okay, good. I'm showing you these things to give you ideas. I'm not showing you them because I want you to do the island model. If you do the island model, fantastic. But I'm not saying that because I want you to do the island model. I'm saying this because I'm giving you a set of ideas that people do. And then feel free to do whatever the hell you want. These are just ones that are noteworthy enough that people talk about them. Come up with your own. If it works really good. So 2 years ago, I had, why can't I remember his name? This is really bad. Jacob, I want to say. I can't remember their name. It's escaping me right now. They did a final project, and it was a really good idea. In the end, it didn't work really well. But I thought it was a fantastic idea, and they did their honors thesis on it. We just shoved them into an honors thesis and be like, they just did this really cool thing. Let's just have them carry on doing it and see where it goes. I'm not convinced the idea is that terrible. I think maybe there could be a couple of tweaks to it. But, like, you never know. Have fun. See what you can come up with. Be creative. I'm not showing you this because you should do this. I'm showing you this because it gives you ideas about what one could be doing. Hopefully that's clear. The only thing that matters is the high-level framework. We have selection, we have fitness, we have encodings, we have genetic operators. That's it. There are cellular EAs where you kind of have this topology and you only allow things to like mate with things that are adjacent to it. Why? Because you could. Novelty search. Now this one's a big one. This is probably one of, in my opinion, the most important contributions to evolutionary algorithms. That's not the word I want to use. It's probably one of the more big, significant contributions that was kind of like a paradigm shift. When we learn about it, you're probably going to think like, yeah, duh. But hindsight, it's a really interesting idea that basically starts to emphasize differentness as being important. Not necessarily better fitness, but differentness being important. Now, we're going to be evolving based on some diversity metric while also considering what a good fitness is. But for this example, we're going to talk about evolutionary art. Perfect, because it's just after what you're doing. It's almost like this was planned. So talking about evolutionary art is great because there is no easy fitness metric. Okay? There is no, just pump it through your fitness function. The fitness function is this subjective thing where maybe you've got a bunch of people. This is also in the context of Pick Breeder, which I talked about yesterday, where it shows people a bunch of pictures, they pick what they like, genetic operators are applied, it does it again, and they can play this game forever until they're done, they're bored, and then you get these pictures that change over time. And you can get these like taxonological trees, I don't know what the right word is. The taxonomy trees of like how the pictures evolved over time. What I mean is, we might start with, a set of pictures, and someone was playing this game for 10 minutes, and they ended up here. And then someone else comes along and they start playing the game, and they didn't start from anything. They just started from scratch, and they end up here. And then, you know, someone starts playing again, but I start picking up where this person took off, and maybe, I don't know, I go over here. And then someone else picks up where they went off, and they take it down a different route than I did. And then someone picks up from here. So you end up getting this, like, this, what's the word I want to use? Like, speciation tree of seeing how things evolved. You can find a common ancestor, but from there you can see these interesting splits. So, it's easier to talk about novelty search with something like evolutionary art because there is no really obvious, measurable fitness function that we could just pump into a function in the computer. That does not mean that novelty search is not applicable everywhere else. It absolutely is, and it's really important. So, and you might remember seeing these pictures. I was talking about these yesterday. It's the same research group that produced the pick breeder stuff. So they had these pictures get generated by people. And actually, let's see what they said. Stepping stones. The lineage illustrates the progression of seemingly unrelated images that led to a seminal pick breeder image in just 47 generations. As a metaphor for solving ambitious problems such as example demonstrates the importance of preserving stepping stones even if they do not resemble an a priori objective. Let's decode what that means. So, the picture there was obtained with an evolutionary idea of the people playing that game. They have this picture. Clearly, an evolutionary process would work to start from a mishmash of images, of just like abstract colors and shapes and light and whatnot. Someone clicked and they got to that like skull image. An evolutionary process did it. If you design a GA to just throw this and just try to measure, try to make it match that based on some image distance metric, the closer it is, the better you are in terms of fitness, you're screwed. You're not going to get it. You won't. But they found that, and here's a couple examples of, okay, this is the image. They wanted to evolve this. They couldn't. They couldn't. You can see that it was making it there, but it couldn't make it. It couldn't quite get there. That butterfly in that skull could very easily be obtained. Were clearly obtained through an evolutionary process, but as soon as they tried to like re-engineer it by taking the humans out, you couldn't do it. So that's weird, right? So the idea that popped up is, okay, so we have to think fairly abstractly here. And I really should redesign this image to kind of have like better colors that show a gradient. But let's say we are looking at the fitness landscape from the top down. All right? As we move that way, the closer we are to that top splotch there, that's better. In terms of, like, that's closer to that picture, let's say. So the closer we are to the top right corner, the better. But we also kind of have these, like, attractors that want to keep the evolution kind of like following these lines. Okay, so at any point, we have, imagine like if I have a population of 100, I have 100 spots all over here. And I want them to get to that top right spot, but they can only, but they're like kind of stuck around these lines. I know this is like weirdly abstract, and I'll show you examples very shortly. But the idea is, I want to get here, but I'm kind of stuck along these. So, let's say I start our evolution with 1, 2, 3, 4, 5, 6 things in our population. Over time, they'll evolve. Okay, maybe you get some that evolve down one route and some that evolve down another route. If we're somewhere in between this process, okay, let's say we've got our population that's kind of stuck here. If something from the group that's going down this route and something from the group going down this route mate, maybe they end up out here in that landscape. But because of these funny attractors, it's kind of not measured as good. So we need to get to the top right, and sure, that point is probably closer to there, but it also kind of has to follow these like trenches, these trenches towards it that go that way. Okay? Any questions? Because I realize this is weirdly abstract, right? Raise your hand if you're like, okay, I'm following you, but where is this going? Raise your hand if you're like, I don't know what the hell he is. Okay. Hopefully we're getting somewhere though. So just 1 second. Over time, we're moving, like we're going down these trenches, and then we get stuck at those ends. Because those ends are closer to the top right by the crow flies, right? So they're pulled along there, but they're still kind of like stuck in those trenches. So you have a question?
Yeah, like maybe it would be a bit helpful to explain kind of like what's going on mathematically, like because I see what you're trying to explain like visually, but like I have no idea really how this would be implemented.
Let's see if I can. I'm going to try a bold thing and see if I can kind of draw what I mean better than this.
Okay.
Better than what I did in 2 seconds in Microsoft Paint. No making fun of them. So, I have I realize that might be somewhat covered, but do you kind of see? So, now, that's me trying to recreate what I have. So, let's say now, though, like, I want to get here. This is better. But also, we've kind of got these, like, clouds around here. Remember, we're looking top down. Thinking of like a topography map, right? Where you kind of see like elevation. And these are kind of like sucking it in. Even though, I want to get there, but it's still, there's this like unavoidable force that's pulling me in here. And these like extend out as we go. So you can kind of think of like a mattress, right? I'm stepping on a mattress, and I'm stepping on a mattress, and I have these two like indentations. This is one of my feet, top down, not like that. And this is another one. Same thing here. We've got this like attractor. It's kind of sucking us in towards this trench to someone standing on a mattress. And then we have one here as well. So the problem is, unless, like, between here and here, there's going to be a boundary where if I'm on one side of that boundary, I'm going to be attracted to one versus the other. If I draw something if I draw it like from the side, if I have a hill and another hill, this point is that point. If a ball gets put here, which way is it going to go? Well, this way. If I put it here, which way is it going to go? This way. Here, which way is it going to go? That way. Here, it's going to go that way. So there's a hump we got to get over. So, so take that idea and apply it there. Imagine these attractors there. Now, in terms of what it means mathematically, it's just this is the shape of this space. And think of it as like, yeah, I'm stepping there. And the function that describes this space, which I have no idea what it is, but it looks like this. I'm standing on a mattress, and it's got these things, and we're kind of, like, we want to get over there, but we're getting sucked into that part. If, like I was saying, we have a bunch of points that, are here, maybe they're going to mate with one another and, make progression towards there because it's closer to that point. At the end of the day, there's still this pull that way, but there's a stronger pull down. And I'll have things going like this. and they'll start going that way. But there's nothing stopping this guy and this guy from producing an offspring, and maybe the offspring kind of like pops up over here. But again, that's going to be, it's still going to be attracted somewhere back that way. It's still getting pulled in until finally over time, we get a bunch of points that are kind of floating around here and a bunch of points floating around here. Again, top down. Imagine it's something like this, but we're bird's eye view and it's two-dimensional, right? Every once in a while, we'll finally get here, these two mate, and then boop, they're over here. Right? This one and this one, you know, they mated and they ended up there. This one and this one, they ended up here. Suddenly, that differentness, if these things kept mating, they get stuck. If these things are only mating, they're getting stuck. But that differentness, when it came together, was enough to get us over that hump and get sucked to the next one. Did that help?
Yeah.
Cool. So we end up seeing this progression, and then finally we can get there. So this is the idea that's trying to be demonstrated, or pardon me, this is trying to demonstrate with a simplification of what's going on with those pictures. What? No, do I not have? Oh, no. How do I not? Okay. Is that a burp? Who was that? That was impressive. Like resonated, like it came from your chest. Who was it? It was you? Well done. Well done. So, So, I will say that this novelty search idea comes up in a lot of applicable areas. Look, you can see, okay, clearly there's like a simulated robot walking or something. Like, this can be applied anywhere, and it's huge. This is probably one of the bigger breakthroughs, like new big ideas in the field. Everyone was doing their things, and then something happened that brought them here. I don't know. And this is where the novelty search idea came from, right? Ideas came together, then finally we got over this hump where we're like, wait a minute, novelty search is a great idea. Where it's just this emphasis on novelty, this emphasis on differentness. If something comes along that's new, that's interesting. If we have a new child pop up in our population, it's a permutation. Maybe it doesn't have as good of fitness, but it's different. And that differentness matters. That differentness adds information to the system. Because if they're all the same, the amount of information kind of converges. But as soon as something new comes along, ooh, something interesting. So it's kind of a flip on the way of thinking about, like, it's not all about fitness. Really, this novelty is really important. So I don't know why I can't find it. I'm really disappointed. Again, I'm going to complain that it's Google's fault.
Yeah.
Google. All right, whatever. Let's just go back to this. No. The idea here, so they use novelty search. Why can't I find this? I know it's in the actual original paper. No. Okay, this actually might be it. I don't think this is it. Maybe it is. Crap. Okay, it's not the one I'm looking for. The idea is as soon as they started to try to evolve these images, where it wasn't all about how close are you to that best thing? How close are you to the image we want you to get? As soon as they kind of threw that out the window, and they were just like, okay, we want to get there, but look for different things. It scared me. Look for different things, and allow those different things to like reproduce, but to encourage that novelty, and suddenly they were getting it like that. So this novelty search, big idea. Big important idea that can really give you some interesting things. It tends to be really good for applications that are a little more open-ended. Like that artwork stuff. Like the robot walking. We're like, well, what's a good program? I don't know. Right? Yeah.
There was something, I don't remember where I saw it, but someone was talking about this like robotic competition that they went to, and their robot, like it broke or whatever, wasn't working the way they wanted it to, like the night before. So one of the guys on the team just suggested, why don't we just make it go forward for 30 seconds? If it hits a wall, turn a random amount of degrees and just do that over and over and over and over again until it gets to the end of the maze. And it got to the end of the maze. It wasn't as fast as some of the ones who obviously were designed to remember the maze layout and whatever. But like, it's just by doing something different than what you just did, you still ended up getting where you needed to go, even though that robot had no idea that it needed to get to the end of the maze. It was just like, I'm just gonna do this and see what happens.
So the robot like went like this, got stuck, spun, went like this,
Yeah.
got stuck, spun,
Yeah,
like that.
Just like over and over until it
Got
there.
there, yeah. Do you see the image I used on Moodle for the course? Who here knows what that's from? Okay, all right, now I get to show you. I swear to God, Google is effing with me. Because I can't find anything anymore.
I was wondering if it's because you're using like a computer. No.
Well, no, the browser knows who I am. Perfect. Okay. So, they were having fun with evolving robots. This was done with an evolutionary algorithm. I wouldn't recommend designing this with an evolutionary algorithm. Like, if I were doing this, I'd use other forms, but whatever.
What
I think it was an evolutionary strategy.
would you use instead?
I don't know. I'd think about it a little longer.
No.
Actually, a lot of fun things, though, are taking place with novelty search in this space. So what they were doing is they're like, well, okay, it's learned, but what happens if we change the structure? Can it adapt? And so, yeah, it did. So they changed the mechanics of the bodies, and yeah, it was learning. And it learned through evolution. Look at that one, it's strutting. That one's amazing.
So wait, what's the evolutionary algorithm actually doing in that?
Well, it's changing how it's doing it. You get a sense of like, oh, there you go. Oh, there you go. But look how good it got after 900 something generations. It starts terrible, but it gets better, but it's still terrible. And then there, after 900, it does a pretty good job. It's stable. So of course, like any good computer scientist, you want to say like, how mean can I be? I want to break this thing. There, oh. You know what, I should stop filming now.
Copyright strike.